Hi everyone, and welcome to EE 326, Lecture 27. Today I'm going to be continuing the discussion of two-stage op-amps, and you can find this in your book in section 13.1. Okay, let's get started. As we discussed last time, we introduced this small signal model for the two-stage amplifier. And then we also introduced this derivation. We didn't actually go through the whole derivation, but if we went through the derivation of doing KCL at nodes 2 and nodes 1, and then combine the two equations to get rid of VI2 here, we'd end up with this as our transfer function. And this tells us the relationship between the output V out and our input VI differential. And what we can see right away is that we have some terms in the numerator and denominator indicating we might have some poles and zeros. As for reference, this is equation 13.24 in your text. The numerator is slightly different, but I just think it's clearer to show it this way. It's really not that much different. And so there's not much intuition in this equation. So to generate intuition, we're going to have to make some approximations based on what we know about frequencies and capacitor sizes and things like that. All right, let's start looking at this equation a little bit more closely. Okay, the first thing we can notice is that this term on the left here, this represents our DC or low frequency gain. And you can see this sort of makes sense. This is a GMR. So each stage is contributing some GMR to it, right? And they're both inverting stages, so that's why we have no negative sign in the front. The next thing we notice is that we have this term over here. And this gives us you notice there's a negative sign here. This gives us a right half plane 0. So the 0 here is just by inspection is at GM, just write this a little bit neater, GM2 over CC by inspection. I'll talk more about the consequences of the fact that it's in the right half plane. And now we have in our denominator here, right, we have two poles. So we have two poles because of this s squared term, right? Because it's quadratic, we know we're going to have two poles. So just to summarize here, our low frequency gain is GM1, GM2, R1, R2, and our right half plane 0, omega z, is equal to plus GM2 over CC. Okay, now to discuss a little bit more about the effect of this right half plane 0, just a little reminder of what the Bode plot is going to tell us. So I want to look at the magnitude and the phase of the Bode plot response of a right half plane 0, again, where we have a 0, but it has this negative sign associated with it. So like a normal 0, right, when we take the magnitude of this and we reach the 0 frequency, we're going to start increasing with a slope of plus 20 dB per decade. Again, in this particular example, our 0 frequency is at GM2 over CC. So that's not very different, right? We expect zeros to go up to increase after the 0 frequency. All right, now what about the phase? We typically think of a 0, at least a left half plane 0, as having a positive phase shift, but because this is in the right half plane, we end up with a negative phase shift. And so as we look at our Bode plot here, we get a phase shift of minus 90 degrees, right? Minus 90 degree phase shift from this right half plane 0. Now you can imagine that if we have this in our circuit, a negative phase shift like this is going to have problems for stability, right? That's going to take away from our phase margin if this 0 is close in frequency to omega p2. So we're going to have to address that. We'll see that in just a second in our Bode plot. So, all right, so now what we need to do is try to figure out where the poles are. We have a sense of the right half plane 0, we have a sense of the DC gain. What about the poles? How are we going to do that? So first what we can do is we can say that the denominator here, d of s, is this product of two terms, 1 plus s over omega p1 times 1 plus s over omega p2. Obviously, we don't know what omega p2 and omega p1 are at this point. And so if I expand this, I get 1 plus s times 1 over omega p1 plus 1 over omega p2 plus s squared over omega p1 times omega p2. And now the basic idea of the approach we're going to take is we're going to say, oh, okay, so this term here sort of matches up with the s squared term, and this term here sort of matches up with the s term, and then we start making approximations. That's the basic idea. And the first approximation I'm going to make, I'm going to say, let's assume omega p2 is much, much greater than omega p1. Now, that's reasonable, assuming we have a compensated op-amp, which is what we're dealing with here, a compensated op-amp, that we have the second pole is going to, the first pole is going to go down in frequency, second pole is going to go to a higher frequency, and so it's safe to assume that omega p2 is much higher than omega p1. As a result, if we look at the second term, 1 over omega p2, it's going to be small compared to 1 over omega p1. Therefore, we can write that d of s, under this condition, is approximately equal to 1 plus s over omega p1 plus s squared over omega p1 omega p2. Now, if we make this assumption, what we can do then is say that omega p1, or 1 over omega p1, is approximately equal to this term in here, right? So if we write that, we can say that omega p1 then is approximately equal to 1 over, and then I'm going to just copy that term. So that would be C1 R1 plus C2 R2 plus CC times GM2 R1 R2 plus R1 plus R2. Now, again, let's assume that R1 is on the order of R2, which is reasonable. These are basically output resistances, so we're going to assume they're, let me just put a parenthesis here to complete this. Let's assume R1 is on the order of R2. What can we see in this equation? So R1 and R2 are about the same. The only term that has an R1, R2 product, which would therefore be the largest term most likely, is this term in here. So let's assume this is a dominant term. Let's assume that's a dominant term because of the product of R1 and R2. Now we can approximate omega p1 and say it's approximately equal to 1 over R1 GM2 R2 CC. So that's our approximation for omega p1. Now, let's just do a little sanity check. Does this make sense that that should be the pole location, the dominant pole location? Well, if we look at this term in here, that would be GM2 R2 times CC. That's really a Miller multiplied CC because the gain of the second stage is approximately GM2 R2, right? So we have this term is really A2 times CC, right? That's what this term is. So it does make some sense. This becomes a 1 over RC, where the C is the Miller multiplication of CC by the gain of the second stage, which is GM2 R2. Okay, so now that we have an approximation for omega p1, let's see if we can determine what omega p2 might be. So we have omega p1 as our approximation, and we have this equation for the total denominator. And so if we equate this omega p1 times omega p2 to this s squared term, then what we see is that 1 over omega p1 omega p2 is equal to C1, C2 plus CC times C1 plus C2 times R1, R2. And now if we substitute this value of omega P1 into here and we solve for omega P2, what we end up with is that omega P2 is now approximately equal to GM2 CC over C1 C2 plus CC times C1 plus C2. So that gives us our equation for omega P2. But let's make some further approximations, okay? Let's assume C2 is much, much greater than C1. Now remember, C2 is going to include a load capacitance, so this is generally a safe assumption. Now let's also assume that CC is much, much greater than C1. So we're saying is the compensation capacitor is going to be much greater than the parasitic capacitances at that first internal node. Again, a reasonable approximation. So if we do that, we can see that our dominant term here becomes CC times C2, right? Because those are the two large capacitances. And then we can say omega P2 is approximately equal to GM2 CC over CC C2, and this goes away. And so this would be that omega P2 is approximately equal to GM2, so it should be a 2, over C2. That's interesting. So what that means is that our second pole location has gone to a much higher frequency than what we would have originally expected. This is pole splitting. This is the, I mentioned earlier we were going to derive pole splitting, but this is it. So we can see that omega P2 goes to a very high frequency, and then omega P2 is going to go to a lower frequency. Now, again, let's see if this makes any intuitive sense like we did for omega P1. Can we draw any intuition from this? So let's look at our circuit again. Remember, we have our compensation capacitor here. And now what we're saying is that the omega P2 is C2, which, let's call this, remember, C2 is a combination of Cl and all the other parasitics here, right? So it's that the total capacitance at this output node is C2. And our small signal model is the total capacitance. So how do we end up with this value here of GM2 over C2, right? Well, one way we can think about it is that at high frequencies, the compensation capacitor starts to short. And if CC starts to short, then essentially what we've done is we've turned M6 into a diode-connected device. Now, if M6 becomes diode-connected at high frequency, remember the impedance seen looking into a diode-connected device is approximately 1 over GM6. So if we looked at the pole at the output node, we'd see that that's omega P2 should be approximately 1 over the output resistance times C2, which is approximately 1 over GM6 times C2, which is approximately GM6 over C2. And if you go back in your notes, you'll see that GM6 is equal to capital GM2. So this does actually start to make some sense here. So we can see that at high frequencies, M6 starts to look diode connected and presents a low impedance, and therefore we get a very high pole frequency. Okay, so in summary here, in terms of the poles and zeros, we have a dominant pole, omega P1, which is 1 over R1 times this Miller multiplied version of CC. We have a second pole, omega P2, at the output. And this happens because CC shorts, and we start to see a diode connected device at the output. So we have a low impedance at the output node. And finally, we have a zero at GM2 over CC, and that zero is really caused by this compensation capacitor. And again, it's important to note that this is a right half plane zero. Okay, so let's look at the Bode plot now for this, now that we have a sense of where these poles are and where the zeros are, and see if there are any issues. Okay, so this is an approximate Bode plot, and we can see magnitude and phase. So notice that I have labeled here, I've labeled omega p1, omega p2, and omega z in both. And I've made some assumptions here. Made the assumption that omega z and omega p2 are considerably higher frequency than omega p1. Notice I didn't put in the 0 dB, or at least I didn't mean to put in the 0 dB line. I shouldn't have labeled that as 0 dB. I just want to make this more of a qualitative a slide here, not necessarily quantitative for phase margin. So what can we notice? Well, we notice that at the second pole, our magnitude starts to roll off. But at the zero, it starts to flatten out again, right? So it's going down at minus 20 dB per decade. And then in this little section in here, it's minus 40 dB per decade from the second pole. But then when we hit the zero, we're back to minus 20 dB per decade. So we get a slowdown in the roll-off. Our gain is not rolling off as quickly as it was if we did not have the zero. Now, let's look at the phase response, okay? Remember, this zero is going to contribute a 90-degree phase shift. So we're going to start to see a phase shift in here from omega p2. Now in this middle section, we're going to get a contribution from omega p2 and omega z, both 90 degrees. And so now we're going to see a total phase shift in here of an extra 180 degrees, right? And so our total phase at the output, at the end here at high frequency, is going to be minus 270. So you can see our phase is rolling off much faster because of omega z, but our gain is rolling off slower because of omega z. And this has to do with the fact that this is a right half plane zero. And so in the next lecture, we're going to learn techniques to try to deal with this. You can see that the right half plane zero is going to give us a smaller phase margin and potentially an unstable amplifier. So we're going to learn techniques in the next lecture about how to solve this problem. Okay, and the last thing I would like to talk about in this lecture is the unity gain frequency. This will give us some relationships we can use in terms of design if we want to go about designing a two-stage amplifier. So we have omega p1, omega p2, and omega z, right? For a reasonable phase margin, we need omega z and omega p2 to be higher than the unity gain frequency. We saw that on the previous slide. Those have to be high in frequency or our phase margin will be low. So if we assume those are high in frequency, then we can approximate this as a single pole system, in which case the unity gain frequency is just A0 times omega p1. And so we could write then that omega t is approximately equal to GM1 R1 GM2 R2, that's A0, times omega p1, which is 1 over R1 GM2 R2 CC, and that's equal to GM1 over CC. I'm sorry, CC. So what we need for stability purposes, right, we need omega p2 and omega z to be higher than omega t. So let's start with omega z, and we can write that GM2 over CC must be greater than GM1 over CC, right? Therefore, GM2 must be greater than GM1. So that gives us sort of one design equation. We want the transconductance of the second stage to be larger than the transconductance of the first stage. Now we can also look at the relationship between omega p2 and omega t, and we can write that GM2 over C2 must be greater than GM1 over CC. Again, this is another design constraint we can use when helping us if we want to design these and how we're going to eventually pick the size of the compensation capacitor relative to the capacitances that already exist in the circuit. Okay, that's it for this lecture, and I'll see you next time. Thanks.